Hey everyone, and welcome to this explainer. Today we're going to break down a concept that is the absolute heartbeat of modern artificial intelligence. I'm talking about Shannon entropy. And listen, we're going to approach this with the exact mindset of a data scientist. So forget any notion you might have that this is just some abstract theoretical math concept. It's really not. In our world, entropy is a hard-nosed critical engineering tool that we use for quantification and resolution in machine learning. Literally, without it, we wouldn't even be able to define what learning actually means for a neural network. It's that important. So let's jump right in. Here's our technical briefing manual for today. We're going to cover the problem of uncertainty, the mathematics of surprise, visualizing flatness, entropy in machine learning, engineering failure modes, and we'll wrap up with the research perspective. All right, section 1, the problem of uncertainty, and how we go about quantifying information content. So, in machine learning, uncertainty is basically our fundamental enemy. To defeat it, we have to be able to quantify the exact information content of a given signal. And to really grasp why this matters, we kind of need to look back a bit. In the 1940s, engineers were using fixed-length telegraph codes, meaning if you had 4 possible messages, you sent 2 bits, absolutely regardless of how likely each message actually was. It was, frankly, incredibly wasteful. Then, in 1948, a Bell Labs engineer named Claude Shannon completely solved this. He realized that information is inversely related to probability. Think about it for a second. Rare events carry a massive amount of information. If I tell you the sun rose today, well, you've gained 0 information. But if I say the stock market just crashed, that's rare and it's highly informative. Today, in modern machine learning, we use Shannon's exact mathematics to measure the disorder of our models, which lets us compress them into confident, actionable decisions. This right here brilliantly illustrates what we call the compression insight. Take a look at the first item. It's a completely predictable string of A's. Because you know exactly what's coming next, the uncertainty is incredibly low. You can compress this down into a tiny, low-resolution package. We call this a state of low entropy. But that second item, that chaotic string of random letters, is highly unpredictable. You can't compress it easily at all because the exact information content, the uncertainty of what the next letter will be, is extremely high. And that is high entropy. Moving on to section 2, the mathematics of surprise. Reading the gauge. Okay, so the absolutely crucial point is right here. We're talking about the surprise meter. The self-information, or let's just call it the surprise, of a single outcome x is calculated as the negative logarithm of its probability p. I want you to literally visualize a physical gauge in your mind. As the probability p gets lower, meaning the event becomes more and more rare, the needle on our meter swings violently into the red zone. That's high surprise. The negative log perfectly captures this mathematically. As probability approaches 0, the surprise scales infinitely. On the flip side, what if we have a trick coin that lands on heads 100% of the time? The probability is exactly 1. If I flip that coin and tell you, hey, it landed on heads, your surprise is exactly 0. You gained 0 new information, right? Because you already knew what the outcome was going to be. But here's the thing. In data science, we usually don't just care about single isolated events. We care about the entire distribution of possibilities. And that brings us to Shannon entropy, represented by h of x. It is simply the expected, or average, surprise of a probability distribution. We calculate this by taking the weighted average of our surprise meter readings across every possible outcome. Basically, it tells us, on average, how unpredictable our entire system is. Section 3. Visualizing flatness, the expected average surprise. Let's look at a classic low entropy case. In this scenario, outcome A is practically guaranteed. Visually, you can see this as a single towering spike. Now, imagine pouring a liquid, let's call it surprise, into these bars to see how much they can hold, based on our negative log calculation. Because this outcome is so overwhelmingly predictable, the expected surprise is incredibly low. A tiny, tiny volume of surprise fills this chart. There is almost 0 uncertainty here. Now, this perfectly illustrates the exact opposite, our high entropy case. All 3 outcomes are equally likely, making the distribution perfectly flat. If we run that same fill animation here, the surprise liquid heavily fills all these flat, uniform bars. Because you literally cannot confidently predict the outcome, the average surprise sits at its absolute mathematical maximum. So, the best mental model to hold on to is this. Think of entropy as the flatness meter for a probability distribution. Imagine your model's outputs as a pile of sand on a table. If it's just a flat layer scraped evenly across the table, you have high entropy, maximum uncertainty. Training a classifier is really just the engineering process of taking that flat pile of sand and forcing it into a towering spike. You're actively trying to minimize the flatness. All right, Section 4, Entropy in Machine Learning. Let's look at some operational implementations. When you actually look under the hood, you'll find that entropy is structurally baked into almost every algorithm we use. In reinforcement learning, like soft actor-critic models, entropy is literally added right into the reward function. We dial it up to financially incentivize the agent to stay uncertain, which forces it to explore its environment rather than just getting stuck doing the same safe thing over and over. In classification networks, we minimize cross-entropy loss to force the model to make confident, spiky predictions. In decision trees, we greedily split the data based on information gain, which is just calculating the maximum possible reduction in entropy. And in transformers and large language models, the softmax layer that outputs those final token probabilities, that is mathematically derived straight from the maximum entropy principle. Let's talk about the concept of temperature in large language models, because it builds perfectly on what we just covered. When you adjust the temperature in something like ChatGPT or Claude, you are literally reaching into the math and manually turning that entropy dial. A high temperature, mathematically, flattens the output distribution, which raises the entropy. It makes the model far more unpredictable and therefore more creative. A low temperature, on the other hand, sharpens the distribution into a spike, decreasing entropy and making the model highly deterministic and repetitive. Section 5, Engineering Failure Modes. This is where the math actually breaks in the real world. These are the primary failure modes you absolutely must watch out for in production. First up, the log-zero NaN bomb. If your neural network outputs a probability of exactly 0, calculating the log of 0 gives you negative infinity. Multiply that out and it evaluates to NaN, not a number. Your training loss becomes NaN, your weights instantly corrupt, and your model dies right there on the spot. You always have to add a tiny epsilon value to prevent this. Second, confusing discrete and continuous entropy. Differential entropy for continuous data can actually go negative, which totally baffles engineers who are expecting a positive gauge reading. And finally, FP16 precision limits. The log of a very small probability is a small negative number. When you multiply that out in half precision on a GPU, it often underflows right to 0, completely destroying your uncertainty metrics. Let's trace the actual compute steps right on the silicon. You take your input probability array, compute the element-wise natural log, multiply the original probabilities by those logs, sum the array, and then negate it. Now, mathematically, that's super simple. But operationally, if you're calculating the entropy of a massive large language model with, say, 100,000 token vocabulary, allocating and moving those massive arrays around just to do element-wise math creates a severe memory bandwidth bottleneck on your GPU. The compute itself is cheap, it's the memory transfer that actually limits your speed. Finally, Section 6, the research perspective, syntactic versus semantic uncertainty. This quote perfectly captures the current bleeding-edge limitation in the field. Entropy cannot distinguish between a confident truth and a confident hallucination. See, Shannon entropy is absolutely brilliant at measuring structural syntactic uncertainty. It measures the shape of the probability distribution, but it is completely 100% blind to the actual meaning or semantic accuracy of the data. An LLM might output a beautifully low entropy, highly confident prediction for the next word, and that word could be a complete and total factual hallucination. Which leaves us with this final, somewhat provocative thought. If a generative AI outputs a completely hallucinated image, or a beautifully written but entirely false sentence, how do we calculate the entropy of its actual meaning? Shannon solves the problem of transmitting data perfectly back in the 40s, but the next generation of data scientists is going to have to figure out how to solve the problem of quantifying the uncertainty of meaning itself. And that's a wrap on Shannon entropy. I hope this technical briefing helped you see the math not just as some textbook formula, but as the fundamental flattens meter that powers modern machine learning. Thanks for joining me on this explainer. I'll catch you next time.